And so we, let's see, I'm going to disappear from here for now. Uh, there we go. And we will go on to explain this. So after a short introduction here, what we have is the idea that we have behind this is, you say, automating the process of modeling and mechatronic systems um, can be achieved by the use of two processes. First, a systematic modeling techniques for modeling the system in any of the domains. And then the second one is the use of software to automate the process. So I will do it that. Okay. So let me get to some of the pictures because this is what is all about. We put a very simple system in here. We have a cart with another mass on top of it, and we are going to say, okay, I need to do a computer simulation of this model. First, the mechanical side, okay? So in here you have that using the, we could do this several ways. You could use the block diagram. You will have to do the following thing. You will have to use the, let's see, you have to identify the elements to make up the system. You have to draw the free body diagram, apply the principles of physics to derive the differential equations, and then you have to generate a block diagram. Once you do that, you enter the block diagram in Simulink. That is how we will do it. Yeah. Okay, so here we go. We do the free body diagramming here, and then put the forces on it, and then we write the two differential equations like this. No problem. This is then the normal way, and then using the equations and a block diagram, you will generate the model in Simulink. And once you do this, this block diagram may look like this. See? This is the block diagram that we use in Simulink. And from here, we could pick up any of the outputs that we want. These are from the manually derived differential equations. Here you have a simulation of the of this, to put out the. These are the two signals that you see in there. The position and velocity for both of those. So okay, once you have done this, we go on this section 2 that says modeling process with direct programming and integration of the differential equations. So in this case, what would we do? Another possibility would use double integration of the equations that we obtain from the free body diagram. It will create manually a computer program. So we identify the elements, draw the apply the principles, then program into something like this. You could do it in MATLAB or so, and there you have the equations, and then you do the integration. And if you do that, you will have to program this into MATLAB on a simulation language, and then do that, obtain the response this way. But here, section 11.2, it says we're going to automate the process using bond graphs. And here's the outline for doing that. We say, okay, this is the process that we use for mechanical systems. Identify what kind of elements make up the system. Identify, let me see if I can identify what kind of elements make up the system. Lay out a bond graph showing how the elements are connected, keeping in mind the constraints. And then CAMG would generate automatically the differential equations of the system, the state space models, the functions, and you can also do the block diagrams from those equations that CAMG produces. So what do we do here? This is where it is the heart of the chapter here, but in this case applied to mechanical systems. So let's go back to the first example, to my example that we have in here. This is the karting here, and then you have this other mass. So this would be an I element, this would be a C, an R element, and so we recognize the different kind of elements that we have in there. Okay. So we have these different elements. Now the second one that we pointed out is we are going to put one velocity for one junction for each distinct velocity. So that's step 2. So we have this one, and we have this one, and then we have the reference velocity. So you have it in here. And then we lay out this one junctions like that. And once we are here, we attach the physical elements that move with those velocities. Now in that case is this one right here. Yeah. So I think what we need to do is to first lay out the ones and then put out the elements that see those velocities right away. That's this step. Then the next step is to represent the zero junctions, the relative velocities or velocity differences with zero junctions in such a way that you have the velocity of the cart minus the wall represented by this zero, and that also is the difference is also another one. So in here you have the difference between the velocity of the cart minus the little one is going to be this one. Once we do that, we attach the elements that move with the relative velocities. In this particular case, you will have the element that you see in there. You would have the C and the R elements are these ones. Let me go back in here to make sure these are between these two, and between these two, and between these two. That's what the C and the R elements are. So you could complete a bond graph model like this. I may venture to see if we can do it um, next to the model here and just use our ability to get this picture by itself, and then we'll redo this real quick together with the explanation as we have it in here. And we're gonna do in here, we'll put this to file. We need to do paste, yeah, so we're gonna paste this picture in here. What I was trying to tell you is that we will use a one junction. It would be nice if we could do it right on the bond graph model. I think because I have the ability to do it in different color, I am going to give it a try, okay? So everything that is red belongs to the bond graph. So this is the velocity. If this is M1, I don't remember, we did it, let's see, yeah, this was M1, and this was M sub 2. Okay, so we put a one junction for the velocity, distinct velocity on here, and then we put one junction for the velocity over here. Yeah. So in here we have we need to put another one junction here, right there. So those three. Then the second step was to attach the elements that see that velocity. We're gonna say this is the I element with value m sub 2. Okay. And over here, this one, we're gonna put the I element with value m sub 1. And over here, this is going to be my source of flow with value SF, the source of flow. And then you say the next step was to do the relative velocity. So we did like this minus, let's see, this one, see, this minus this will produce a relative velocity, which I call it a 1, that says this was velocity of m1 minus velocity of m sub 2. Okay, and then this other one over here, you have, this is the 0 here, and in here you will have a one junction. Finally, the last step was to attach the C and the R. We attach to the elements that see the difference, like this, and then we attach it to this one, like this. See? There you go. And that's how we built the model for the mechanical system. So I think we could go back to where we were before, explaining the rest of it. So this is, as far as the mechanical system is concerned, we have applied those steps and we ended up with this bond graph. We implemented into the CAMG software. This is how it would look. Now, from here, the computer goes and creates this M file that contains the differential equations of the system, and together with the initialization file, which is shown over here, with this you produce the answers that we obtain exactly with the Simulink model. But the difference here is that it's a computer-aided design system method, because we didn't do the programming. The computer, in this case CAMG, produce all these M files that are the ones that MATLAB works with. M files are basically command files to MATLAB, and produce the simulation. But now that we have done this, I want to move in and do the same thing but for electrical systems. Now remember that we are trying to establish a situation where the method is consistent for all three of them. And so you see here you have three loops, and the first thing we do is to put the one junction for each distinct current, and then attach the elements that see those currents. And that's what this is. And now we use zero junctions to create the current differences, and that's what this is. See the current difference between these two, the current difference between these two, and the current difference between these two. And that's what you're seeing here, right there. Oh, sorry, one more step, right here. And then we attach the elements that we see those current differences, which is the same thing like in the mechanical system, to attach the elements that see the relative velocities, and then you have complete the bond graph modeling here. Finally, if you do this same thing using for the hydraulic systems, you have in here the system, and in this case I'll try to do the same thing as we did before with the mechanical system. Try to draw it on the system itself. 3 ones in there for the 3 flows. We put the flows first. Now we put the elements that see those flows right there. This is, of course, to the ambient temperature is like a source effort with effort 0. But you see, after you do this, we're going to create the flow differences with this, and flow difference between these two. And then we're going to attach the elements that see those flow differences. In this case, the C here and the C over here. And we are done with this. See, with this process. And that's what you see here. Here you see it a little bit simplified. We simplified this through power element that we have. Sorry, right here. Right there. So that's how we complete the model for the hydraulic systems. So I think that is the process that we have experienced for all three systems, for hydraulic systems, for electrical systems, and for mechanical systems.